Okay, welcome back. We're on page 385 talking about dynamic programming. Okay, so the first example on page 386 is calculating the Fibonacci numbers. You guys remember back in chapter 2 when we did this, where it's basically, a value plus a value, right, over and over again. And so this one, unfortunately, because we're using this technique, when I want to get to the sixth version, the sixth Fibonacci number, I really have to have an awful lot of 1 and 2, then I get to 3, and then I use 2 and 3 to get to 4, and I use 3 and 5, 3 and 4 to get to 5, and 4 and 5 to get to 6, right? So to get these numbers, I have to go through like a whole bunch of steps to get to Fibonacci number 6. And so I'm actually using an awful lot of these things over again. There's an awful lot of duplication. Like, how many times am I going to calculate Fibonacci 2? Well, this is 1, 2, 3, 4, 5 times. Like, geez, that's a heck of a lot. Wouldn't it make more sense to have a scorecard? Some sort of an array that kept track of what the previous values are, so I speed things up. So this is kind of sort of like dynamic programming, kind of sort of. Actually, it's not a very good example of dynamic programming, but bear with me. So, lots of duplicates. So an alternative approach would basically use an array to keep track of the previous 2 values or so. Okay, so here's the algorithm, and it's not that fantastic. I just have this little value guy. And so I just record the value and then keep moving. All right, so I update the value and then just record. So it maintains state information in there and cuts down on the amount of processing. Okay, so dynamic matrix multiplication, page 388. Now, you know how to do matrix multiplication, right? We've done that before. We have a matrix and a matrix. Remember how these things are the associative property, where if you change the order of the matrix, the size of the result is going to come out different? Remember all that? Okay? Right? So the order in which you do the multiplication is important. So what if I told you I wanted you to multiply 4 different matrices, and you just went, oh, okay, 1 times 2, and then take that and multiply times 3, and takes that and multiply times 4. Right? I'm done. I did what you told me to do. I multiplied them. But wouldn't it make sense to have an extra processing step, which is where the dynamic comes in, the extra processing step where you try to figure out the optimal order in which these things go, okay? The optimal order. Okay, so here's a cool little example of if I did 1 times 2, then I end up with 3,500. If I did 2 times 3, I end up with 700 multiplication. Then 3 times 4 equal to that. So if I did them in this order, 1 times 2 times 3, it'd be 63. If I did 2 times 3 times 1, I'll end up with that many. So when I'm multiplying them all together, here are my choices. One of the choices is 3,100. The other choice is 24,000. So yeah, some dynamic programming where you first figure out the order in which to do these things would be really, really handy, don't you think? Because it'll cut down my processing a lot by first figuring out the optimal order in which to multiply, and then I multiply whatever it is. I multiply 2 times 3, and then times 1, and then times 4. Okay, in that order. Okay? So there's a technique to pick the order, and the algorithm is on page 390. I'm not going to bring it up on the screen. Remember, there's 2 parts to this. The first part is to find the optimal order, and then after you've done that, do the math. We already know how to do the math part, so I'm moving on. There's another one called Floyd's all-pair shortest path algorithm, page 391. And it says, find me the shortest path between all nodes. Basically, I want a spider web kind of a thing. I want a connection between all nodes and the shortest path between each one of the nodes. Okay? So I could just use the shortest path algorithm, just go through every single one at a time. Go through that for each pair, right? That would be a little weird, but okay. But you could use a matrix multiplication technique from chapter 8. Where you multiply times the previous results for every node. That way you can remember where the previous nodes were. In other words, I don't have to go over something a second time. Unfortunately, this only generates just the total length, the optimum length. Like, it'll say, okay, when we're done, after I've connected all these guys together with their total links, the answer is 12. And if you really wanted to know the path, the actual list of nodes, well, then you'd have to come up with another recursive algorithm that would decode that thing. Okay, figure out what the actual path is from the numbers that you create. There's as an algorithm on page 393 that basically shows how you store the length in an array so that you don't have to recalculate it over and over again, and hence that's why it's a dynamic algorithm. Okay, let's keep going. Page 393. They talk about the dynamic version of the backpack problem. So, okay, remember how this thing works is, remember I have things coming off no, this is backpack. Backpack is the one where I have a size and then a weight or a value associated with it, and I want to maximize the things in here. So one way to do this is to create a two-dimensional array, one with the object, whatever the object number is, like 1, 2, 3, 4, 5, right? They're arbitrary as heck. And the other would be their weight, okay? Weight or their size. So here is the object numbers, and then here is what their weight and size are weight and value are. And so, if you start off like this and figure this thing out, remember I'm after 50, right? So I can't do all of this. Okay. So we fill the array based upon the values already in the array. That's what makes it dynamic. In other words, I start here and then I go, oh, I need to do add a 2 to it. Okay, great, that'd be 80. And then, okay, and so this would be, 55 plus 80. And, just what makes this dynamic is as I'm filling in the array, I'm using the previous values in the array to come up with that. Kind of sort of makes sense. Okay. So I don't actually need to fill the whole array. I can stop after a while. I can stop after I get to 50. I don't need to keep going, right? Okay. In other words, if I blow, by the way, this can't be 50. I have no idea what because this element number 3 is already at 55. I don't remember what the top value is for this. 100? I don't know, whatever it is. 200, pick a number. So anyway, the bottom line is I don't have to keep filling the array once I hit the magic number. Let's just say it's 100, okay? Which means I could stop 200 then, got it. I could stop right there, I could stop right there, and I could stop right there. So I could just not bother to fill out the other parts because I know they blew it. Okay? Kind of makes sense? And there's a really cool website article that I found that talks about how to do this in our technique we just talked about. Create a two-dimensional array. The row number represents the items, and the other represents the weight or the value, whatever it is. And then I go through and fill these guys up. And here's the thing. This is the part that's a little complicated. So we're tackling a sub-problem consisting of just, this. And there are two options at this point. We can either include an item or not include an item. And then we compare that. And then we just keep going and going and going. So here's their thing. And so in their case, it looks like the maximum value. It looks like 40 is their maximum. I can't tell. Anyway, the idea is they're doing the same thing, and they're filling in the array, and then they stop when they get to the point where they don't need to bother to go any further. Okay, kind of sort of makes sense, I hope. So here's the math logic on how to make it work. Okay, after it's all been populated, and then here's the final thing on how this thing works. Anyway, it's pretty doggone cool. Okay, we have reached the end of this chapter and actually the end of the course. And the next time you see me, it'll be for the review for the final exam. Okay, see you guys then.